Hello everyone. So today we will be looking at Form 4 Chapter 4, the Periodic Table of Elements, Part 3, Group 1 Elements. So before we start going into Group 1 Elements, let us have a short recap session of what we've learned in Part 1 and also Part 2. So in Part 1, we have learned that in the Periodic Table of Elements, the elements are arranged according to ascending order of proton number, right? From the left to the right, from the left to the right, and so on. And in part 1, we have also learned that in the periodic table of elements, we have horizontal rows and also vertical columns, whereby the vertical columns are known as groups. And these groups are determined by the number of valence electron. And we have also learned that the horizontal rows are known as periods. And these periods are determined by the number of shells occupied by electrons. Okay, and in part 2 we have learned about group 18 elements, and the special characteristic that group 18 elements have is that all group 18 elements have achieved either stable octet or duplet electron arrangement, right? For helium, it has achieved stable duplet, and for everything else, it has achieved stable octet electron arrangement. And because they have achieved stable electron arrangement, they are unreactive. They are known as inert gases or noble gases, meaning that they are unreactive. They do not react with other elements or substances because it is already stable. Okay, so that's what we have learned in part 2. Now we're going to go to part 3, where we're going to learn about group 1 elements. Right, group 1 elements. So these are group 1 elements right here. These are group 1 elements. So before we start going into group 1 elements, as usual, let's look at the overview a little. So in this part, we're going to learn about group 1 elements, right? Group 1 elements, and we're going to learn about the physical properties and also the chemical properties. In terms of physical properties, we're going to learn about the appearance, conductivity, density, solubility, and hardness, as well as the melting and boiling point for group 1 elements. And for chemical properties, we're going to learn about the reaction of group 1 elements with other substances. And in this part, we're specifically going to focus on the reaction between group 1 elements with water, oxygen, and also group 7 elements, which is also known as halogens. Okay, and we're also going to look at the reactivity, and also we're going to look at how the reactivity of the elements changes going down the group, and also how the physical properties of the group 1 element changes going down the group, as how we have looked at the changes of physical properties going down the group for the group 18 elements, right? It's basically the same. So now we're going to look at group 1 elements, right? Group 1 elements. So these are the group 1 elements that we're going to learn about. And specifically, we're going to focus on lithium, sodium, and potassium. Okay, in our syllabus, we're going to focus on lithium, sodium, and potassium. And these group 1 elements, actually, they have a special name, such as how group 18 elements are known as noble gases or inert gases. Group 1 elements also have their own special name, and it is known as alkali metals. They are known as alkali metals, and we'll go into why they're called alkali metals later on. So here, we're going to discuss the physical properties of group 1 elements or alkali metals. And so here I've attached a photo of lithium metal that I've obtained from Google. And from this photo, you should be able to deduce that the lithium metal is shiny gray in color. So that is the physical property in terms of appearance, right? We're going to look at the appearance. So in terms of appearance, the group 1 elements or alkali metals are shiny gray. They are shiny gray metals. Next, we're going to look at the conductivity, right? Conductivity. And group 1 elements, right? They are metals. They are metals. They are known as alkali metals. And so since they are metals, they are good conductors. They are good conductors of heat and electricity, right? Because they are metals. And generally speaking, metals are good conductors. However, the special thing about group elements is that in certain aspects, they are not like other metals. They are unlike other metals in a few aspects. Firstly, do you notice anything weird with this photo? So this is actually a photo of lithium metal in water, right? And supposedly, you know that metals have a high density, right? And if they have a high density, it means that they should sink to the bottom, right? If we have water, metal should sink to the bottom. So what's happening here? Why are they floating? Well, that's because group 1 elements, unlike other metals, they have low density. And their density, right, density of group 1 elements is lower than the density of water, which is why it's floating on water. Okay, that's the first thing, right? Secondly, usually, right, other metals are hard, right? Other metals are hard, are usually hard, right? If you take a piece of metal from any part of your house and you try to cut it with a knife, you're gonna find it very difficult to cut that piece of metal. But for group 1 elements, for alkaline metals, they are actually soft. And even if you just use a knife, you can cut through the lithium metal or sodium metal with ease. It's going to be very easy to cut it because it's soft. So that's the second thing. And thirdly, right, we know that usually metals have high melting and boiling points, right? However, group 1 elements, they have a low melting and boiling point. But this is with respect to other metals. Okay, with respect to other metals. If you compare group 1 elements with, for example, group 18 elements, group 1 elements are still much, they still have much higher melting and boiling point lah. However, group 1 elements, they have low melting and boiling point when you compare them with other metals. But it's still higher than, for example, group 18 elements, because it is still held by strong metallic bond, right? The forces of attraction that holds metals together is strong metallic bond, which allows the melting and boiling points to be high, right? However, when you compare with other metals, it is relatively low. So that would be the physical properties of alkali metals, okay? They are shiny gray metals, and like other metals, they are good conductors of heat and electricity, but unlike other metals, they have low density, whereby they are less dense than water, they are soft, and they have low melting and boiling points. Physical properties, done. So now we're going to actually compare the physical properties between the group 1 elements going down the group. So in terms of, we're gonna compare the elements in terms of atomic size and also the melting and boiling point going down the group. So when we're going down the group, as usual, we know that the proton number will increase, which means the electron number will also increase, and also the number of shells will increase, right? The number of shells occupied by electrons will also increase. So what happens to the atomic size? So like how we have discussed in the group 18 elements section, right, in the last video, the atomic size of the elements going down the group will increase. Why? Well, we have discussed this in group 18 in the previous video with group 18 elements. It's basically the same concept. For example, let's take two elements. Let's take lithium and sodium, right? Let's take two elements, and let's go ahead and draw the electron arrangement. Let's go ahead and draw that, right? So for lithium, okay, it has 3 electrons, 3 protons, meaning it has 3 electrons. Therefore, the electron arrangement is going to be 2, 1. How about sodium? Right? Sodium has 11 protons, meaning that it has 11 electrons. Therefore, the electron arrangement is going to be 2, 8, 1. Now, let's draw the electron arrangement. So, we're going to have lithium here. And then we're going to have sodium here. Right, so if you look at the electron arrangement, what you will be able to find is that the atomic radius will increase, right? The radius of sodium is much larger than the atomic radius of lithium. Why is this? It's because lithium has 2 shells occupied by electrons, whereas sodium, right, it has 3 shells occupied by electrons. Therefore, this causes the atomic radius to increase. And when the atomic radius increases, the overall size of the element will also increase. So the atomic size will increase when you go down the group, right? How about the melting and boiling point? What happens to the melting and boiling point when we're going down the group? Well, we know that when we want to compare the melting and boiling point going down the group, first we need to know whether it's a metal or non-metal. So in this case, group 1 elements, or also known as alkali metals, are metals, right? They are metals. So since they are metals, they are held together by strong metallic bond, right? However, when we go down the group, we know that the atomic size increases, right? The atomic size increases. So when the atomic size increase going down the group, we know that for metallic bond, the forces of attraction will actually decrease, right? The forces of attraction between the atoms will actually decrease. And when the forces of attraction between the atoms decrease, less heat will be required to overcome the forces of attraction, right? And when less heat is required to overcome the forces of attraction, the melting and boiling point will decrease. So going down the group, the melting and boiling point of group 1 elements will actually decrease, right? If we go back to the overview here, right, we know that for metals, they are held together by strong metallic bonds. When the size increases, right, they're held together by strong metallic bond. When the size increases, the force of attraction will decrease and less heat will be required. For non-metals, they are held together by weak van der Waals force of attraction, and when the size increases, force of attraction increase and more heat is required. This is something that we've gone through in part 1 and part 2, and we're still talking about it in part 3, which is why I have put a bit of emphasis on this overview since part 1, because if you are able to understand this concept since part 1, you should have no problems understanding it in part 2 and also part 3. So now we are done with the comparison of the physical properties between group 1 elements going down the group, right? Going down the group, the atomic size increase, and this is because if we draw the electron arrangement, we'll find that going down the group, the number of shells occupied by electrons increase, which causes the atomic radius to increase, and therefore the atomic size will increase. For the melting and boiling point, it will decrease, and this is because when going down the group, the atomic size will increase. And when the atomic size increase, since it's a metal, it's held by metallic bond, the force of attraction between the atoms will decrease, and so less heat is required to overcome the force of attraction, and the melting and boiling point will decrease. Right. So next we're going to look at the chemical properties and the reactivity down the group. Okay, so group 1 elements, they are reactive. They are reactive, and this is because they have not achieved stable electron arrangement, right? For example, let's say we have sodium. Sodium has 11 protons, meaning it has 11 electrons. So the electron arrangement is 281, right? And so in order to so if we look at the electron arrangement, we know that it has 1 valence electrons. All group 1 elements have 1 valence electron. And because it has 1 valence electron, it has not achieved stable electron arrangement. Therefore, it has to react with other elements, with other substances, in order to achieve stable electron arrangement, whereby it has to remove this 1 electron, 1 valence electron, in order to achieve stable electron arrangement. And so when this happens, it will become a positive ion, right? So for example, sodium, right? Sodium originally has 11 protons, 11 electrons, and this is the electron arrangement. But when you release 1 valence electron to achieve stable octet electron arrangement, the number of protons is still the same. It's still 11 protons, but it has only 10 electrons now because it has released its 1 valence electron, right? So if we look at this, it has 11 protons, 10 electrons, which means it has 1 proton more than the electron, right? So what does this make it? It makes it positive, because protons are positive while electrons are negative. Therefore, sodium is no longer just an atom, but it is an ion now, Na+, the plus representing the positive charge of this ion, right? Because it has 1 proton more than its electron. So that is in terms of its chemical property, right? It is reactive, and it releases it has 1 valence electron. So in order to achieve stable electron arrangement, it will release this electron in order to achieve stable octet electron arrangement, and in that process it becomes a cation, a positively charged ion. So now let's discuss the reactivity down the group. So when we want to discuss or compare the reactivity of elements down the group, what we have to know is that we're going to compare about the tendency of the atom to either release or accept electrons, right? If we go back to the overview here, reactivity, right? Reactivity down the group, we have to compare the electropositivity, which is the tendency to donate valence electron to achieve stable electron arrangement to become cation, or the electronegativity, which is the tendency of the atom to accept electron to achieve stable electron arrangement to become an anion. So in terms of group 1 elements, since it has only 1 valence electron, we know that it will become a cation, and it will release electron or donate electron, not accept electron. Therefore, the reactivity down the group depends on electropositivity, which is tendency to donate valence electron to achieve stable electron arrangement and become a cation. Okay, so we're going to compare the reactivity going down the group by comparing the electropositivity of each element going down the group. That's what we're going to do. So going down the group, what do we already know? We know that, number 1, we know that the atomic radius increases, right? If we go back to the physical property here, we know that going down the group, the atomic radius will increase because the number of shells will increase. And because the atomic radius increases, let's just copy this diagram. Let's just copy what we've drawn earlier, right? So because the atomic radius increases, the distance between the nucleus and the valence electron, right, will also increase. And when the distance between nucleus and valence electron increase, the forces of attraction between the nucleus and valence electron will decrease. Why are we talking about the nucleus and valence electron here? Well, we know that the center of the center of foundation, or not the center of foundation, the center of gravity or the center of attraction is actually the nucleus, right? The nucleus, which holds most of the mass of the atom, right? Because it's comprised of protons and neutrons, right? Protons and neutrons. It contributes to the overall mass of the atom. Electrons are very light. They don't really contribute much to the mass of the atom. And because of that, we know that the nucleus is the one that produces the so-called pulling force of this atom towards the electron. What we're trying to say is that the nucleus pulls the electrons, right? So if the atomic radius increases, the distance between the nucleus and valence electron increases, we know that since the nucleus is further from the valence electron, the force of attraction between the nucleus and valence electron will also become weaker. It will decrease. So if it becomes weaker, then the attraction between the nucleus and the valence electron will become loose. So this valence electron is more easily released. So the tendency to donate valence electron increases, meaning that the electropositivity will increase, and therefore when the tendency to donate valence electron increase, the reactivity will also increase. So going down the group, the reactivity will increase because the atomic radius will increase, and therefore the forces of attraction between the nucleus and valence electron will decrease, and the tendency to donate the valence electron will increase, and therefore reactivity will increase. Okay, because when it donates the electron, it will react with other substances in order to form a new compound, and so that it is able to achieve stable electron arrangement, right? Okay, so next we're going to look at group 1 elements reactions. So in this chapter, for group 1 elements, we're going to learn about the reactions of these group 1 elements with 3 substances. Firstly, with water. Secondly, with oxygen. And thirdly, with group 17 elements, which are also known as halogens, right? Much like how there's a special name for group 18 elements, which is inert gases or noble gases, and for group 1 elements it's called alkali metals, and so group 17 elements also has its own name, which is halogens. And it is here that we're going to discuss why group 1 elements are called alkali metals. Oh, and one more thing is that for our syllabus, we're going to focus on 3 elements, which is lithium, sodium, and potassium. Okay? Right. So, first, we're going to discuss the reaction between the group 1 elements with water. So, in order to describe the reaction, we're going to actually look into the experiment the experiment that we'll do in order to determine the reaction. So what are we going to do? The first step of this experiment is that we're going to take out we're going to take out an alkali metal, could be lithium, sodium, or potassium, from a bottle of paraffin oil. Okay, and then we're gonna actually cut this metal. We're going to cut it using a pair of forceps and also a knife. Okay, pair of forceps to hold the metal, and also a knife. So this is a knife. These are a pair of forceps. We're gonna take out a piece of metal, and then we're gonna cut a small piece of alkali metal, which can be sodium, can be lithium, can be potassium, using knife and pair of forceps. So this is the first thing we're gonna do. Second thing, we're gonna take this small piece of lithium metal that we've cut, and we're gonna put it on a filter paper. We're gonna put it on a filter paper to dry it. We're gonna put the piece of small lithium alkali metal that we have cut on a piece of filter paper to dry the metal. Next, what are we gonna do? Next, we're gonna take a basin. Okay, we're gonna take a basin, and then we're gonna add water. We're gonna add water so that it's filled with water. And then we're gonna take this lithium alkali metal, and we're gonna put it on the water slowly. Put alkali metal into basin of water. And then what we're gonna do is we're going to observe the reaction. We're gonna observe the reaction, and we're gonna see what happens to the alkali metal on the surface of the water. And of course, you're going to see that the metal will actually float on the surface of the water. It won't sink, and this is because of the physical property that we've looked at earlier, which is it has a low density which is lower than the density of water. So it will float, and we're going to look at the reaction between this metal and the basin and the water in the basin. And once the reaction is over, right, we still have the water in here, right? We're going to take a piece of litmus paper, red litmus paper, and we're going to test this solution that has been produced with the red litmus paper to test it. So if you have retained some of your knowledge from Form 1, Form 2, Form 3, or even your primary school, you know that we have two types of litmus paper. We have blue litmus paper and we have red litmus paper. Now, red litmus paper is to test whether it is basic or not, whether it's alkaline, right? And blue litmus paper is to test whether it's acidic. So if the red litmus paper turns blue, it means that it is basic, right? It means that it is basic or alkaline. And what you're going to see is that it will turn blue. Okay, it will turn blue, which means that it is basic or alkaline, and that is exactly why these group 1 elements are known as alkali metals. So to test it, whether it's basic, and you will see, yes, it is going to turn blue, meaning that it is alkaline or basic. So this is the experiment that you will probably do in school, or maybe not, depending on you know, the circumstances at the point in time. But what you have to know is these steps, because they can ask you to describe the experiment in your examination. And secondly, you need to know the observations and also the reaction equation. So what are the observations of this reaction, right? What are the observations? So generally speaking, right, before we go into detail of each of the observation for each alkali metal, which is lithium, sodium, potassium, generally what's going to happen is that when you put this alkali metal on the surface of the water, it's going to react with the water and it's going to form a colorless solution. And this colorless solution is going to turn red litmus paper blue, which indicates it is basic. Okay, it's going to form a color solution and it's going to turn the red litmus paper blue. So generally speaking, that would be the observation that you're going to observe for all three metals. Now we're going to go into detail for each, like lithium, sodium, and also potassium. So for lithium, right, for lithium is, well, if we look at what we've discussed earlier, right, going down the group, the reactivity will actually increase. So lithium is actually the least reactive metal in the group. So for lithium, what's going to happen is that it's going to move slowly. It's going to move slowly on the surface of the water until it dissolves to form the colorless solution, which turns red litmus paper blue. And you're also going to see a little bit of gas being emitted, and we're going to discuss on what that gas is later on. Okay, so how about sodium? For sodium, it's much more more reactive than lithium, right? So instead of moving slowly, it's going to move at a fast speed. And then because it's more reactive, it's not just going to emit gas, but it's actually going to burn. It's going to burn with yellow flame. It's going to burn with a yellow flame. And then next you have potassium. Potassium is much more reactive than lithium, and it is more reactive than sodium, right? Because it's below sodium in the group. So if sodium moves at a fast speed, potassium is going to move at very fast speed, and it's going to burn with a purple flame. And another thing is that you're going to see a lot of gas being emitted, and this gas will actually react with the burning of the potassium to produce a pop sound. Now you should already be able to guess what this gas is, right? We have done a lot of tests since, you know, your lower secondary on a lot of gases that we learn in chemistry, and there is only one gas which we learn, if the gas is burnt, it will produce a pop sound. So what is that, right? What is that? It is presence of hydrogen gas. Okay, so from this experiment, what you should be able to deduce is the reactants is, of course, the alkali metals and also water, and it's going to produce something that's going to dissolve to form a colorless solution, right, which turns red litmus paper blue. That's the tips. And then you know that there's a presence of hydrogen gas, so the products would be something which is going to dissolve to form a colorless solution, which is basic, and also hydrogen gas. That would be the product. So what is the reaction equation? Let's do the reaction equation here. Reaction equation. So the reaction equation is, okay, let's take lithium. Okay, let's take lithium. The reactants is the alkali metal and also the water, right? lithium and water, and it's going to produce products, which is something here, and we know that there's hydrogen gas. So what is this X? The X is actually lithium hydroxide. That is why it is basic, because lithium hydroxide is a base. It is going to dissolve in the water to form an alkaline solution, which is basic, and which is why it turns the red litmus paper blue. Okay, so now we have the reaction equation, but is it balanced? No. So we're going to balance the equation. So over here, we're going to look for the odd number first, odd number. So here we have 1 lithium, 1 oxygen, 1 hydrogen. But over here we have 2 hydrogen, 1 oxygen. Here we have 1 lithium, here we have 2 hydrogen. So in total, over here we have 3 hydrogen, but here we only have 2 hydrogen. So the odd number will be on the products, not the reactant. So in order to balance the equation, first we have to make the odd number into an even number. So to do that, should I add the number here or here? Well, this is even, this is odd. So of course we're going to add it here instead. So let's try 2. Let's try 2 first. So if we put 2, we're going to have 2 lithium, 2 oxygen, 2 hydrogen plus 2 hydrogen, 4 hydrogen. And if you look at the reactants, we have 2 hydrogen, 1 oxygen, and 1 lithium. So over now, the one that has an odd number is the reactant, right? We have 1 hydrogen here, but we have 1 oxygen here, but 2 oxygen here. So we have to add a 2 here. Now, what do we have? We have 2 hydrogen, 2 oxygen, and 4 hydrogen. Here we have 2 lithium, 2 oxygen, and 2 plus 2, which is 4. So our hydrogens are already balanced. Our oxygen is also already balanced. Only our lithium is not balanced yet. We have 2 lithium here, but only 1 lithium here. So we put a 2 here and done. This is our reaction equation. And this is quite important as well. And you should know how to balance equations, how to form equations. And if you don't know, it's okay, you can watch my video for Form 4 Chapter 3 Basic Concepts. Is under 30 minutes. You can cover most of the basic concepts for Form 4 Chapter 3, which is related to the calculations, how to determine the charge of the ions, how to determine the equation of the compound, right? Not the equation, the formula of the compound, how to write balance equations, how to balance the equations, and so on. So if you are still weak in balancing equations, I highly recommend you to watch that video, because it's going to take less than 30 minutes of your time, and you're going to be able to learn how to form these chemical equations and how to balance them. Right, next. Oh, before that, let's take a recap. Let's take a recap of what we have learned here. Right, so we learned the reaction between alkali metal with hydrogen with water, whereby the first thing we need to do is we're going to take out a piece of alkali metal, and then we're going to cut a small piece of the alkali metal using a pair of forceps and a knife, and then we're going to dry it in a filter paper, and then we're going to slowly put the alkali metal into a basin of water, and then we're going to observe what happens in the reaction between alkali metal and water, and then it's going to produce a color solution, and we're going to test the color solution using a red litmus paper, which we know will turn blue, indicating that it's basic. And these are the observations. Generally, it will form a color solution which turns the red litmus paper blue. For lithium, it is the less reactive, so it will just move slowly on the surface of the water and eventually dissolve to form the color solution. For sodium, it's more reactive, so it moves at a fast speed and burns with a yellow flame. For potassium, it is much more reactive, so it's going to move at a very fast speed and burn with a purple flame, and also produce a pop sound, which indicates the presence of the hydrogen gas. Okay, and here's the reaction equation. So 2 moles of the alkali metal will react with 2 moles of water to form 2 moles of the alkali metal hydroxide and 1 mole of hydrogen gas. Okay. Next, we move on to the second reaction, which is the reaction of the alkali metals with oxygen. Right. So the way that you start the experiment between oxygen and alkali metal is the same as how you would start the first reaction, which is what we would do is we would take out a small piece of alkali metal and then we would cut the small piece of alkali metal using a knife and also a pair of forceps. And then we will use a filter paper to dry the alkali metal. That is how you would start the second experiment as well. So let me just copy this and paste it here. Alright, so after you dry the piece of alkali metal using a filter paper, what you would do is you would take a combustion spoon. So this is how a combustion spoon looks like, and then you would place the alkali metal onto the combustion spoon. So put the piece of alkali metal in the combustion spoon. Okay. And then what you would want to do is you would heat the combustion spoon along with the alkali metal until the alkali metal here starts to burn. Okay, until it starts to burn. And once it burns, what you want to do is you want to immediately transfer it into a gas jar. So here's a gas jar. Right, so you transfer it and insert it into a gas jar which is filled with oxygen gas. Right, it is filled with oxygen gas. This is a gas jar and this is a combustion spoon. Alright, and then what you want to do is you want to wait until the reaction is completed, meaning it stops burning. So once it stops burning, right, let me just copy this. Okay, so once it stops burning, what you want to do is you want to actually add water. You want to add about 10 centimeter cube of water into the gas jar, and then you shake this gas jar to dissolve the product of the reaction. Okay, and then once you have the the solution, right, the solution in the gas jar, once you have the solution, which is produced from the product of the combustion between alkali metal and oxygen dissolved in 10 centimeter cube of water, you will want to test this solution using a red litmus paper. A red litmus paper. And the function of this red litmus paper is basically the same as the first reaction, which is to test whether the solution produced is basic, right? So this is how you would carry out the second reaction, which is the reaction of alkali metals with oxygen. Now, what are the observations, right? What are the observations? So first we go with the general observations, all right? So general observations. So generally, what you would see, no matter what type of alkali metal you use, is that basically when you burn the alkali metal in the combustion spoon, it will burn and produce a white powder. Okay, so this product here is a white powder. You will produce a white powder, and this white powder is actually a metal oxide, right? For example, if let's say we used lithium, right? Lithium, and then we have oxygen, right? Oxygen. So what you would actually produce is lithium oxide, which is Li2O, right? Because lithium is in group 1, therefore it has 1 valence electron, and it will produce, so when it is ionized it will become Li plus. And for oxygen, it has 6 valence electrons, so it will receive 2 electrons to become an anion with a charge of 2 minus. So if you cross it, you would get Li2O, right? Yeah, okay. Now, so that is the general observation, right? It will burn and form a white powder, which is a metal oxide. Okay, and then if we look back on the experiment here, what we did was that we actually dissolved the product, which is the metal oxide, with 10 centimeter cube of water. So this metal oxide will actually dissolve in water to produce solution which turns red litmus paper blue, which indicates that it is basic, right? Basic. So that would be the general observation of the reaction between alkali metals with oxygen. Now let's go into detail for each alkali metal, which is lithium, sodium, and potassium. So for lithium, what you would notice is that it will burn slowly. It will burn slowly with a reddish flame. Right, it will burn slowly because it is the least reactive, and as we know, when we look at a fire, the more reddish or dark the color, it means that it has more impurities, and this is because lithium is less reactive. Therefore, what you will see is that when you burn the alkali metal, which in this case is lithium, you will see that it burns slowly with a reddish flame. Now, how about sodium? For sodium, since it is more reactive than lithium, right? Since it's more electropositive, so it will actually burn brightly. It will burn brightly with a yellowish flame. Because it's more reactive, so it will be but it will burn brighter and also with a brighter flame, which is yellow. Yellow is brighter than red. And then next you have potassium. How does potassium what's going to happen to potassium? Well, potassium is more reactive than both sodium and lithium, so it will burn very brightly with a purplish flame. It is the most reactive one, so it will burn the brightest with the brightest flame. Okay, it will burn the most brightest and also with the brightest flame. And then for the reaction equation, actually what we already wrote the reaction equation just now, but let's write it again. So you have lithium, well, actually any alkali metal, it can be lithium, sodium, potassium, and you're gonna react it with oxygen, and then it will produce lithium oxide. Sodium reacts with oxygen to produce sodium oxide, and potassium reacts with oxygen to produce potassium oxide. So this would be for the second reaction, which is the reaction of alkali metals with oxygen. The last reaction, the third reaction, would be the reaction of alkali metals with halogens, which are the group 17 elements. Now we don't have much time to discuss every group 17 element, so we're just going to discuss chlorine, okay, chlorine gas, the reaction between alkali metals with chlorine gas, in which we will burn the alkali metals in chlorine gas. And actually, this reaction, the third reaction, is actually the same as the second reaction, except we will actually substitute the oxygen here with halogenous gas, which in this case would be chlorine. So actually what we can do is we can just copy and paste this entire procedure. Right, we can just copy and paste the entire procedure because it is going to be the same. The whole reaction is basically the same, except we replace oxygen with chlorine. We replace it with chlorine. However, of course, the reaction, the product that is produced will no longer be metal oxide, right? Because we are no longer reacting it with oxygen. Instead, we are reacting it with chlorine gas. So what's going to be produced? Well, the white powder is still going to produce a white powder, but it's not going to be a metal oxide. It will be a metal halide. Metal halide. And the metal comes from the alkali metal, and the halide comes from the halogen. Right, let's say we have lithium with chlorine. Okay, so what will you get? Let's do the cross method, right? Lithium, it's in group 1, it will have a valence electron of 1, therefore it will release 1 electron to become a positively charged ion with a charge of positive. And then you have chlorine. Chlorine is from group 17, therefore it has 7 valence electrons, and so it will receive 1 electron to become a negatively charged ion, which is an anion with a charge of negative or minus. So if you cross it, you will get lithium chloride, LiCl. So Li plus Cl2 forms LiCl, and then you balance the equation. Done. So this would actually be the reaction equation. Let me just put it down here. Reaction equation. Now, how about the observations? Are the observations the same? Well, the answer to that is yes. The observations for the third reaction and the second reaction is the same. So the observation, we can just copy and paste this observation. Except in this reaction, in this experiment, we actually did not test the solution. Okay, we did not test the solution. We did not dissolve the product of the reaction with water, and we did not test the solution with a litmus paper. And this is because the metal halide is a salt and it is not basic. Okay, so we did not test it with a litmus paper, and the white powder that we have produced is not metal oxide, but it is metal halide. So there you go, all 3 reactions of alkali metal covered. Now we move on to the final section of this video before we wrap up the lesson for today. So here are 3 questions, right? So whoever wants to give it a try first, you may do so by pausing the video and coming back once you have attempted all of the questions. Right, so now I shall discuss each question in this exercise. So first, describe the reactivity of group 1 elements going down the group. So we know that going down the group, what happens is that the atomic radius will increase. And when the atomic radius increases, right, the distance, it means that the distance between the nucleus and the valence electron becomes further. The distance becomes greater, and when the distance becomes greater, the forces of attraction between the nucleus and the valence electron becomes weaker or decreases, And so when the forces of attraction between the nucleus and the valence electron decreases, what happens is that electropositivity will decrease, right? Because if the force of attraction is lower, then the valence electron will be much easier to be released or donated. So the tendency, or in other words, the tendency to release electron increases. And so when this happens, the reactivity will increase. The reactivity will increase because when it releases an electron, it will be received by another atom which requires that electron in order to achieve stable octet electron arrangement. Right, so that is the first question covered. Second question, lithium metal burns in excess oxygen to form a white solid. Write the chemical equation for this reaction. So this is the second reaction that we discussed earlier. So the alkali metal used here is lithium metal, and it reacts with oxygen, right? It's burning in oxygen to produce a white solid, which we know to be metal oxide. So let's write the equation, right? We have lithium, and then it reacts with oxygen to produce a metal oxide. So we will have lithium oxide, which is Li2O, right? Because the charge for oxygen is O2 minus, while the charge for lithium is Li plus. And then you balance the equation, and done, right? Third, state the observation for the reaction of lithium metal burning in chlorine gas. So lithium metal burning in chlorine gas. This is the third reaction of alkali metal, whereby the alkali metal used here is lithium metal and the halogen gas here is chlorine gas. So you can state a few observations. First of all, you can say that the lithium metal, right? Lithium metal burns slowly, right? It's the least reactive alkali metal. It burns slowly with a reddish flame. That's the first observation that you can give. Second, you can also say a white solid, in bracket, metal halide, is produced. And thirdly, you can also say the greenish yellow color of chlorine gas is decolorized because it is burnt, right? It is burnt already. It's used up. Alright, so we have done the exercises, and now we're done with today's lesson of group 1 elements. So let's just roughly go through what we have learned in this chapter, in this part. Right, we have learned about the group 1 elements, which is right here, and specifically our syllabus focus on lithium, sodium and potassium. And then we have looked at the physical properties of alkali metals, and from this photo we can see that it is a shiny gray metal, right? It is a shiny gray metal, and since it is a metal, it is a good conductor of heat and electricity. However, unlike other metals, it has a low density, whereby its density is lower than the density of water, which makes it float on the surface of the water. And it is soft. Unlike other metals, you can cut it using a knife, and the melting and boiling points are low when you compare it with other metals. Then we have discussed the comparison of the physical properties between group 1 elements going down the group, whereby going down the group, the atomic size increases, and this is because the number of shells occupied by electrons increases going down the group, and therefore the atomic radius increases, causing the atomic size to increase, as illustrated by these two diagrams here, right? The drawing of the electron arrangement of lithium and sodium, whereby sodium is below lithium in group 1. And we know that melting and boiling point will actually decrease going down the group because group 1 elements are metals, right? They are called alkali metals. They are metals, and metals are held together by strong metallic bonds. However, when the atomic size increases, the force of attraction, which is the metallic bond between the atoms, will actually decrease, right? It is basically inverse. When if it's strong, as the atomic size increase, the force of attraction will decrease. Unlike for non-metals, right? For non-metals, they are held together by weak van der Waals forces of attraction, which will actually increase as the atomic size increase. And when the force of attraction between atoms decrease, so there will be less heat required to overcome the forces of attraction, leading to a decreasing melting and boiling point. And then we have looked at the chemical properties of group 1 elements, whereby we have deduced that group 1 elements are reactive, and this is because they have not achieved stable electron arrangement, right? Because it has one valence electron. And so when the atom wants to achieve stable octet electron arrangement, it has to release that valence electron, and when it releases the valence electron, it becomes an ion. And all the ions in group 1 has a charge of positive or plus. And then we have discussed the reactivity down the group, whereby going down the group, the atomic radius will increase, which means that the distance between the nucleus to the valence electron will also increase, as illustrated by the drawing of the electron arrangement of lithium and sodium. And so the force of attraction between the nucleus and valence electron will decrease, because as we know, the nucleus is the one that actually pulls the electron. So if the valence electron becomes further from the nucleus, then the force of attraction will actually decrease, and therefore the tendency to donate the valence electron will increase, meaning that the electropositivity increases, and so the reactivity increases, because when it releases the valence electron, when it donates the valence electron to another atom or ion, right, it will achieve stable electron arrangement, and so that means that it reacts with another element in order to achieve that, right? One element will actually release the electron, and it will be received by another element. And then we've discussed the group 1 element reactions, which is the reaction of group 1 elements with water, oxygen, and also halogens, which are the group 17 elements. So here we have the reaction between alkali metals with water, whereby first we cut a small piece of alkali metal using a knife and a pair of forceps, and then we dry the alkali metal using a filter paper, and then we slowly put the alkali metal into a basin full of water. And then we observe the reaction of what happens when we do this. And then once all of the alkali metal has dissolved, we will test the solution that is produced using a red litmus paper. And the red litmus paper is to test whether it is basic. And what we will find is that generally all alkali metals, when put slowly into water, will form a colorless solution. And this colorless solution will actually turn red litmus paper blue, meaning that it is basic. And specifically for lithium, since it is less reactive, it will move slowly on the surface of the water until it dissolves to form the colorless solution. For sodium, since it is more reactive, it will move at a fast speed and burn with a yellow flame. And potassium, being the most reactive, moves at a very fast speed, and it burns with a purple flame. And due to its high reactivity, a pop sound is heard, and this pop sound indicates the presence of hydrogen gas. And in general, this is the reaction equation for the reaction between alkali metals with water. Right, so you have the alkali metal, which reacts with water to produce a metal hydroxide and also hydrogen gas. And then second, you have the reaction between alkali metals with oxygen. So you start by cutting a small piece of alkali metal using a knife and a pair of forceps, and then you dry it using filter paper, and then you place it in a combustion spoon, and then you heat the combustion spoon along with the alkali metal until it starts to burn. And once it burns, immediately put it into a gas jar that is filled with oxygen. And then once the reaction is complete, add 10 centimeter cube of water, right? And then dissolve the product, shake the jar, and then test the solution using a red litmus paper. And of course, we have to look at the observations. So generally, when we heat the combustion spoon, all of the alkali metals, whether it's lithium, sodium, or potassium, will burn, and it will form a white powder, and this white powder is metal oxide. Okay, and then after that, since when we add water, it will dissolve the metal oxide powder, and it will produce this solution. So this solution will turn red litmus paper blue, meaning that it is basic, and that is why it is called alkali metals, because they are alkaline. And then specifically for lithium, what will happen is that it will burn slowly with a reddish flame because it is the least reactive, and then sodium will burn brightly with a yellowish flame, and potassium will burn very brightly with a purplish flame. And here is the reaction equation, and I just realized that this is not balanced. There you go, better. Okay, third reaction would be the reaction between alkali metals with group 17 elements. So you start the same thing again by cutting a small piece of alkali metal and using a knife and a pair of forceps, dry it with filter paper, and then put it in a combustion spoon, heat it, and then immediately transfer it into a gas jar filled with chlorine gas. And then same thing, you will produce a white powder, but this time it is not metal oxide, it is metal halide, whereby the metal represents the alkali metal, halide comes from the halogen. Observations are the same, right? It burns and forms a white powder. And then the reaction equation is right here, right? You have 2 moles of the alkali metal reacts with 1 mole of the halogen gas and produce 2 moles of metal halide. Right, so that is all for today's video, which is Form 4 Chapter 4, the periodic table of elements, Part 3, Group 1 elements. I hope that all of you were able to understand everything that was taught in this video. Thank you very much, and goodbye.